So, hello everybody. I'm Sunita Chandarasekaran from University of Delaware. I'm an assistant professor there in the Department of Computer Information Sciences. So this talk is going to be about the validation and verification test suite of OpenMP 4.5 offloading model. And this is work in collaboration with Oak Ridge National Lab. So Swaroop, Oscar, and David Bernhold are our collaborators from Oak Ridge National Lab. Jose Diaz is my PhD student from ECE, UDEL. So we will walk you through, why is this project important, what kind of tests we have built, and what are the experimental setting, and what are the compiler implementations, and so on and so forth. Right, so that's the outline. We give you an introduction about problem statement, contributions, about what is 4.5 offloading, what is the methodology, the design of the tests, what are the types of tests we have written, why we chose what we chose, how is our infrastructure design looking like, what are the result logs, how are the reports, how we generate the reports, and we'll also give you a demo of where we have captured these results in a website and how to go over it and look at the results for your analysis purposes. I wanted to start this off by letting you know that this is part of the exascale computing ECP project SOLVE project, and SOLVE's focus is building this OpenMP programming environment for ECP. So as you can see the stack here, right? So this is your hardware stack, and you have all types of accelerators, all types of heterogeneous systems going on. Hardware is evolving very rapidly. Things are changing very rapidly. And with Summit-like system, you have a lot of on-node concurrency, billions of concurrency possibility in a single node, because single node has become fatter and fatter, right? We're talking about 44 cores, and we're talking about 6 GPUs on a single node. The above this hardware stack is a software stack where the very first layer are your ECP applications, and then comes the different compilers, and then the different runtime layers. In this case, OpenMP runtime, Bolt, and Argobots, and then you have the operating system and so on. So where does our project fit into this entire paradigm is we come over here where we are building the test infrastructure and creating these different test cases in order to be able to validate and verify the compiler implementations of the OpenMP 4.5 offloading features. Right? There are several implementations available, and there are multiple platforms available. So how do you test the quality of the compiler? And we go back and forth with the vendors, and we talk to the OpenMP standard in case we don't follow anything. Sorry, it's the wrong way to say. In case we have questions on the OpenMP specification, right? Or in case we think that this implementation should have been done the other way around just because our test failed, which often sometimes we write a test and we think the test is right and the implementation is incorrect, but only to find out that it's the other way around. So this involves very frequent interactions with the vendors as well as the compiler developers and the OpenMP standard. So I would now invite my student Jose Diaz to talk about the rest of the process.
Hello everyone. My name is Jose Monsalve, and I am the main developer on the University of Delaware side. So I'll start by explaining why are we so focused and interested in accelerator devices. I think this is no surprise for anybody who is coming to this conference, but we see an increase in the power usage, and this will be, for example, in the top 500 list, we can see that the average power of the systems that do report the power consumption is actually increasing. And the problem is, how do we cool down and how do we increase the performance? And the best solution that they have come out with is using accelerators device that will let us use part of the code, that will let us take part of the code and accelerate that segment of the code and obtain more performance for that part. Assuming that that part of the code is important for the rest of the application, then we will get a speed up. So the main challenge here is how do we increase with the limited power that we have, how do we increase performance? And so one option is to feed more devices and do something like single program multiple data, like the way we are doing. On the other side, we have the OpenMP specification, which is constantly trying to adapt to those changes that the hardware is bringing. The problem is, how can we guarantee the specification is made? built by a group of multiple vendors, and try to they try to come up with the features that make sense for everyone and that make sense for the trend. However, they later on take that specification and do the implementation. How can we guarantee that implementation and the specifications match in between the two? So we need to develop a methodology that is not vendor specific, that is more targeting the specification itself, that goes from the words that are in the specification all the way to the vendors, instead of the vendors creating their own test for their own implementation, because that is kind of like being biased about that implementation. So what we want is that we treat the specification as a legal document. The specification should be this bounding document in between the user and the vendors that sorry that without the requirement of them both interacting directly, they can communicate in between each other. So we are somehow like the lawyers of those documents by creating tests that can verify if the implementation is doing what the documents are saying. So we can see the ecosystem as something like this, where we have the OpenMP specification on one side, and we have the running system on the other side. The compiler implementer can use the specification to decide to implement, can use the specification document for its implementation, and now the running system, he knows because of the OpenMP specification, he knows that by just using that particular compiler, he can support that particular implementation. But the user, as long as he knows how to use the compiler implementation, he shouldn't have to learn how to use every single implementation. As long as the user knows the specification, that should be enough in terms of programming in OpenMP. So why not using, for example, the example? So why do we want to create more and more code that could be somehow redundant with the code that is in the examples or the code that each of the vendors is creating? Well, the reason is that the examples do not really try to cover every possible case that is in the specification. They just try to create a single case that will work for the user to understand the specification, but they do not really cover all the possibilities. And it definitely serves a completely different purpose. Why not automatic testing? Why not having something that will just create the test for us? Well, there is a lot of understanding of the words. There is a lot of process of going into the document, reading and seeing if the language that is in the document is the one that they actually are, or if it is clear enough for the user to use or to refer to. So there is a lot of human effort that is required in order to do that. And the vendor tests, they are actually biased. We do not want to replace the vendor tests. I think that each of the vendors, they will have testing as part of their own development cycles, and that's completely okay. But those tests are trying to cover the things that they already know they want to cover and that they already taught in the process of creating the development. So we want to, and also sometimes those tests are vendor specific. Like, let's say that they are doing something with an NVIDIA GPU, then they may use APIs for the NVIDIA GPU, and we want to remain vendor agnostic completely. So we want to move away from that as well. So most of you are probably familiarized with the OpenMP 4.5 of loading, so I will just go really quick over this. And this is just the way that we see the machine as programmers when we are trying to target devices. What we see is we have the host on one side and we have a set of devices on the other side, and those are interconnected in between each other. There is a storage area, like a storage address space for each of the devices, and there is a storage address space for the host. Even though sometimes those storage address space may refer to the same physical storage, the OpenMP specification does not, the 4.5 specification does not say that it has to be different, but sometimes when we use, for example, the mapping, it says that it should seem different from the perspective of the user. However, sometimes the fact that they could be the same makes testing a little bit tricky, especially if we are trying to test something like mapping, or if we are trying to test privatization or things like that. So sometimes it's a little bit complicated. We have to consider some corner cases as well. So we start in the host. The host will go offload segment of the computation, and that starts a sequential thread. That sequential thread can be divided up into multiple teams, into multiple thread teams. Each of them just corresponds to a different set of like a group of threads. However, when we use the teams, we are just creating the master threads. The other threads are there, but they are not doing really anything. This is similar to the parallel, where all the different threads are going to do exactly the same code that is within the teams region. When we use the distribute, what we are doing is we are taking a loop iteration space and we are splitting it up among the multiple master teams. And when we use a parallel for inside, what we are doing is using the rest of the threads in the thread team to spawn computation. And finally, we can do SIMD. And what we do this, if we see this, for example, in terms of the GPUs, we will see that this will be like a wrap. Then we will have a block, a group of threads. Then we'll have a block. Then we'll have a grid, and so on and so forth. So the first two are actually just regions of code, while the other three at the bottom are for loops, for loop kind of code. So what is the methodology that we are following in order to come up with this test? We always start from the specification, and what we do is we take the specification and we read. First, we split it up into the different parts, the different directives that exist. And we took the specification, and what we did was read each of the elements and come up with a possible test, like a testing methodology for a particular part of the specification. So we formulate the test, and then we discuss the validity of that test. If we consider that the test is valid, we go and make a first implementation, and we see if that implementation passes among the different compilers. We tried GCC, we tried Clang, we tried XLC, XLF. We have many of the different compilers, and we check if it is passing or not. If it is passing, we open it up for review. We make sure we always do the two reviews. This one is more about how are we proposing to test, and this one is more about the code itself. Are we actually doing what we proposed at the beginning, and are we generating code that is valid for OpenMP and that can be and that is valid also for the specification document itself? If that is accepted, then we add it to the test suite. If not, then we will have to go and reiterate over this process again. If the test doesn't pass, and we know that the test is valid, it may be because it's a specification issue. Probably the words in the specifications are not clear enough, or it may be because it's an implementation issue, and so we have to go and report that bug to the vendors. And we have actually reported many bugs to the vendors. Some of them have resulted in corrections of the implementations. And sometimes we go and report a bug, and we end up somewhere in between the two, because they said, no, we are interpreting the specification this way, and so we go and ask other people, we ask the community, we make sure that that's also the case, and so on. So our test will look something like this. In this case, we are trying to use multiple devices and see if the map of an array will work with the device class. So we are testing the target data map device. So it will be the target data construct with the device class. So what we do is we create an array with the number of devices and size n. First we check how many devices there are. Then we create an array, and we try to map that array. We iterate over each of the devices, and we try to map a segment of that array that is equal to the device number times n. So we are just taking the whole array, and we are dividing it in segments of n, and each of the segments will go into a different device. And then inside, we are going to create a target region, and that target region will just assign the value of the device variable into the matrix. Now, this is one of the things that, because it's 4.5 and we do not have a way of knowing which device we are at, then we have to use the variable from the loop. And it gives us also a limitation of how much we can test. If we consider, for example, 5.0, they already include a new API call that let us query which one is the device that we are running at. Okay, so there are limitations with respect to how much tests we can do, and I think that those could be some things that may be improved once the 5.0 specification comes into the implementations. And then all we do is we check if the value of the device is the one that we actually expected, and if not, we increase the number of errors. Another test, a little bit more complex, or not complex, but that is trying something with respect to memory, is first private. And the idea here is that if we have an initial value of the privatized variable, and then we have an inner for loop, and we just increment that variable, because it is private within the teams, within the thread in the teams, then the value that we have at the end has to always be the expected value. If we have a data race in this point, then we will see, if we have a data race in this point, then we will see that the value at the end is not the one that we expect. So we use, our tests are codes like this. They are really short. We try to use we have a file that has some macros that allows us to keep them short, to always have the same output. We always point out at which was the line that generated the output, which was the file that generated the output, and we have tried to make it as flexible as possible. So the infrastructure, one thing that we put a lot of attention into was how do we plan for the infrastructure of the test suite. And what we decided was, let's use a Makefile and let's use some scripts that allows us to support the rest of the process. Why Makefile is because it is widely available in multiple systems. Like it's really common for many of the systems, especially for the systems in DOE, to have support for Makefile. So we have a portability across multiple compilers. We have portability across multiple systems as well. We wanted to make sure that most of the tests had the same output and that all the results were easily parsed. So our scripts will organize the outputs in a way that we can parse the log files, and we can present them in JSON file, we can present them in an HTML view that I can show at the end, or we can present them just in the raw format. So we have thought about how we collect the data as well, how do we present the data to the final user, and so on. We organize our folder structure in a way that we have the test completely separate from the rest of the infrastructure. So we create a folder test, but the Makefile is sitting outside of that test. Ideally, is that the long-term idea will be that this Makefile will also allow us to change in between one specification and the other one. So right now we are doing 4.5, so we only have tests for 4.5, but what we are seeing is that once we move, for example, from 4.5 to 5.0, there are parts of the specification that will change also the tests. So some of the tests may not be valid now for 5.0, and they were valid for 4.5. So we have to make sure that we divide them up. But we are trying to keep that as part of the design process of our test suite. In our Makefile allows you also to use multiple flags that let you choose if you want to just have did it pass or fail, or if you want to have some verbosity in the results. Do we want to get the actual line, the execution of the command line that it used? Do we want to create a log system? So we use multiple Makefile options to do selections. You can also, for example, just run the test, just run a single set of tests, or just run a test that has that ends in the word underscore something. Like if you want to do test of all the possible maps, so you can do a star underscore map star underscore and then underscore star, and then that will just run the ones that have the map in the name. So an example, it is as easy as this. You get the test. Some people will argue that there are some errors, and we are working on them. You get the test, you go inside, and you use make, and it will start running, compiling and running the files. So from the git clone to the folder to the make, it is compiling, and then at the end, you're going to see, after the compilation is done, you're going to see when it starts running. Okay. So we also want to be able to split up, for example, the compilation of the test and the run of the test. So we have different rules in the compiler that allows us to split up. Sometimes you want to have, you want to create first the compilation on let's say, the login node, and then the run on the compute node. So we want to be able to also split up the two. So we create the different rules for to support that. And additionally, we have some rules that are for reporting. So if once you get the run with the log flag on the options of the Makefile, you can get the results in JSON, or you can get them in HTML, and it will create a nice view for you. Another thing that we wanted to consider is that sometimes there are system-specific features. For example, where do we get the compilers from? If we are using system modules, if you are using Linux-like modules, you want to be able to load those modules, and sometimes you want to do that loading before each of the tests, before each run. So we also support this as long as you can easily swap the module from one to other. So there are older versions of the Linux modules that don't let you just swap one module for the other one. If you try to load a new module, it will complain because you already have another module. The newer versions of modules will actually let you, it is intelligent enough to figure out which one to unload and which one to replace it for. So that goes into our folder structure. There is going to be a system, a set of system files that you can extend, and you can specify multiple options for those particular files. Any questions? Yes. So all this is running in Summit Dev, Titan, and we are working also in our university system. So because this is part of the ECP project, the idea is that this will be part of the compliance, the acceptance compliance for Summit as well, eventually. Okay, so as I mentioned before, we support multiple results, but I will show at the end how the results look like. So as you were saying, yeah, we are running on Summit, and we are also running on Summit Dev. It's really nice because we are able to extend our test to up to 6 devices when the clauses in the OpenMP allows it. We are also trying to include some tests that are a little bit more functional. So we are trying to include some application tests, like mini apps that are part of the code of the different users in the DOE labs. But that is something that we are still working on. Some of the things that we are seeing. By the way, the version of Clang that I'm reporting in this slide here is a special version of Clang that is homebrewed for Summit and for Summit Dev. So we call it Clang Coral. We have actually run the test on the trunk version of Clang. The results are quite similar. We have tests for Fortran. We have more tests for C right now, but we are trying to move. There are many of our tests that are in the development branch, and we are trying to move them. We have realized that one of the parts that is the hardest to do is that process of making sure that are correct. So we have to constantly be discussing, and sometimes we get stuck into words of the specification, pointing out at which page says what, and then we go back and forth, and that usually takes us a lot of time. So there are more tests in the development branch than there are in the master branch right now. Some of the example of results that we have seen is, for example, for IBM Excel compiler, we realized that the default mapping of some of the enum variables was not the correct one. If we see the specification in this page, it says that if you are doing scalar values, the default mapping should be like an implicit data sharing attribute of first private, meaning that the value that I have here should be copied to the target, but the modification of the target should not be copied back to the host, just because of this first private, right? So if you have an integer, if you have a double, all of these elements, if you do not specify any mapping of those elements, then they should be first private. And so we realized that for enums, they were actually modifying the version of the host. But this was resolved later, or thanks to our team. So we have many more examples. It's just that for the sake of time, we have to cut it in there. But you are more than welcome to visit our website. I'll just go really quick and show you.
So we have a website where we have populated all the tests and the reports and how to navigate through this. This is a home page where we tell you what the project is about, and if you go to the repository tab to your left, third one from the top. Yes. So if you go to that one, we have the structure as to how would you pick this up and where are the, which is the folder, what is in each folder and stuff. And if you go to the results tab, you will see that all the results are categorized according to compilers and systems. So if you scroll up a little, so you can choose a compiler, choose a system, and find out what the compiler results are looking like. And it's going to give you a bunch of report cases. And so it tells you what passed, what failed. So this is open source. Take a look at it. Come back and tell us if we have misinterpreted something, or you would like the feedback, or you love this. All feedback welcome. Say something else?
Yep. Yeah, I just want to mention that this is exactly a HTML report that we provide without the bar, just this segment here. So when you create the report in HTML, you should be able to get a report like this. And I think that this is something we have worked with vendors like AMD, and they really like something like this because it was really easy for them to just get the information that they needed. So it will look something like this. Thank you.